Okay, so this story here is the whole purpose of the story on the screen here is to introduce you to vector equation of a straight line. Here I'm using a two-dimensional line as an example because it is something that you are all more familiar with. Uh, The same concept will be also applicable when we have a line in three dimensions. Okay, so let me repeat the story from the beginning. Okay, so um, I first started by drawing the line on a usual xy plane, right? And I identified 2 points A and B on the line, and I constructed a vector, the vector AB, which is parallel to the line L. Okay, and then I introduced a general point R with coordinates xy on the line L. The general point means the point can be anywhere along L. And so I've labeled several possible positions of R on my diagram. And so my R can be very far up here, it can be somewhere in the middle of A and B. It can also be very far on the bottom left. And so here are several possible positions of R. R can be actually anywhere along the line. Now, I introduce a small letter r to be the position vector of the general point capital R. Then small letter r will be a vector directed from O to R. Then I try to find a path to get me from O to R by involving the point A. And so I use point A as a intermediate stopping point. And so I travel from O to A first, and then I travel from A to R. Now, depending on where my R is located, if my R is located on the right of A, if R is located on the right of A, then the vector that directs me from A to R will be a positive scalar multiple of the vector AB. Right? Because to travel to the upper right, I just need to extend or shorten my vector AB. And that will involve some positive number multiplied by AB. If the point R is located on the bottom left of A, then to direct me from A to R, I will require a negative scalar multiple of AB. Because I will then need to reverse the direction of AB and at the same time shorten or lengthen it. So I will need a negative number for my lambda. Now, to cater for the possibility of R being anywhere along the line, since my R can be anywhere, so to make it possible for us to move from A to R regardless of the position of R, or to include all the possible positions of R to make them reachable, then we should allow lambda to take all real values. And so if we allow lambda to take all real values, then all the possible positions of R will be reachable from A. Right? So the vector lambda times AB, it will be able to direct us from A to R, regardless of where R is located, as long as R is somewhere along the line. Right. Now, if I write it in vector form, like in bracket form, where I sub in the values, what is my OA? OA will be 1, 3. AB will be the vector 1, 2, lambda in R. Okay. Now, it's time to introduce you to the terminology. Okay, this equation here is known as the vector equation of the line L. It's known as the vector equation of the line L because we are having an expression in vector form for the position vector of a general point. Right, so this is clearly an equation that involves vectors because on the left you have position vector and on the right you have a sum of two vectors. So this is clearly an equation in terms of vectors. and we call this a vector equation. Now, looking at the right hand side of the vector equation here, this vector that is multiplied by lambda, we call it the direction vector. So this is a terminology that you need to be familiar with. Direction vector is the vector that is multiplied by lambda. And what is lambda? We call it a parameter. Right, the scalar or the unknown lambda that we allow it to take all real values, we call it a parameter. As you vary the parameter lambda, you are actually varying the position of R. So for example, if you set lambda exactly equals to 1, then your vector equation will lead you to point B exactly. If you set your lambda equals to 2, then it will lead you to a point that is further up. And as your lambda becomes larger and larger, then your vector equation will lead you to a point that is even further up. So a parameter is something that when you change its value, it will lead you to a different point on the line L. Right? And what is this 1, 3 here? This 1, 3 is a position vector of a fixed point on L. It can be any fixed point on L. So here I'm using the point A. If you want to use point B, it's also fine. It's also fine. Okay. So the whole idea of vector equation is this. What is R first? Okay. This R is actually the vector xy. Because small letter r is used to denote the vector OR, and we know the point R has coordinates xy. Okay. Now, okay, so if I write R as a vector xy, 1, 3 plus lambda 1, 2. Okay. Now, if you look at this vector equation, it's actually giving you an expression for x and y coordinate of a point on the line. So you get x equals 1 plus 1 lambda. You get y equals 3 plus 2 lambda. Okay. And for example, when lambda is equals to 1, you get the x coordinate as 1 plus 1 times 1, which is 2. Y is 3 plus 2 times 1, which is 5. And that means 2, 5 is a point on the line. And is 2, 5 really a point on L? It is, because it is actually your point B. So for example, if I change the value of lambda, when lambda is equal to 2, then my x is 1 plus 1 times 2 is equals to 3. Y is 3 plus 2 times 2 is equal to 7. So this means 3, 7 is another point on L. And so is 3, 7 really a point on L? I think you can easily check. It should be a point on L. Okay. Okay. So as a summary, the idea of vector equation is instead of giving the equation in terms of x and y, like instead of writing y equals to x plus 1, this one we call it the Cartesian equation. Instead of writing it this way, we want to describe the line by using vectors. So this R here is a standard symbol. So whenever you see the vector small letter r, it means position vector of a general point on the line. Okay. So the vector equation basically wants to give you a sum of two vectors, where it first leads you to a point on the line, then followed by lambda times the direction vector, so that you can reach anywhere along the line. So the idea is this: for any random line, regardless of whether this is 2D or 3D, the same idea would work. So if this is a line L, the origin O can be somewhere far away. It might be on L, it might be not on L. Let's assume that origin O is somewhere far away. Right. Just pick any point A on the line L. Then obtain a vector from O to A. So you would fill up the vector OA here. And then to make it possible to reach any point along the line L, let's say your R is here, your R is here, your R is here. To make it possible to reach all the possible positions of R, what you need is only a vector, which we usually denote as B, as the direction vector. The direction vector of the line L can be any vector that is parallel to L. Whether it's longer or shorter is not important, as long as it is parallel to L. It can even point in the opposite direction. It doesn't matter. Any vector that is parallel to L can be used as the direction vector. So you would put your vector B here. And then by attaching a lambda to it, it allows you to modify the length. It allows you to modify the length of B. Lambda times B means the B can be lengthened or shortened, or even have its direction changed to become the opposite direction. Right, so once you have lambda B here, it will enable you to reach R, right, by selecting a suitable value of lambda. Right. So for example, if I want to reach this particular R, I just need to take the path OA followed by lambda B. So this is the idea of vector equation. Right. It wants to lead you to a point on the line by taking you to another point on the line first, followed by traveling in a direction parallel to the line. Okay, so if your R is up there, then it will lead you OA followed by this AR. Okay, I don't see any questions so far in the chat, so I assume everyone can digest. If there's anything you want me to explain again, please let me know. Okay, so the same idea here is applicable to the three-dimensional lines. Okay. So for example, I have this line L in 3D, okay, with a point, let's call it A with coordinates 2, 5, 7. And I have a vector parallel to the line, for example, minus 1, 0, 2. Then, if I want to describe a general point on line L, I can use R equals to 2, 5, 7 plus lambda minus 1, 0, 2, lambda in R. And so as I vary my value of lambda, this equation is going to lead me to a different point on the line L. For example, if I set lambda equal to 0, when lambda equal to 0, I get R equals to 257. This means 257 is a point on L. Because the small letter r is position vector. Position vector can be easily converted to coordinates. Right, so when my lambda is set to be 0, the right hand side of my vector equation, it leads me to exactly the point A. Right. If I want to go somewhere else on the line L other than A, then I will need to set my lambda to be some other numerical values. Right, so for example, when lambda is equal to minus 1, my R will be equal to 257 plus 1 minus 0 minus 2. Right, so this will lead me to 3. 5 minus 0 is 5. 7 minus 2 is 5. Right, this means 355 is a point on L. And so my second point could be somewhere here. Right, for three-dimensional lines, the Cartesian equation will not be as simple. Right, for two-dimensional lines, we know that um, the Cartesian equation can be written as y equals mx plus c. But for three-dimensional lines, it won't be as easy because you have x, y, z coordinates to link up. In 2D, you only have x and y coordinates, but for 3D, you have x, y, z coordinates. So the Cartesian equation for a 3D line, it will look more complicated, and that we will cover in page 7. The Cartesian equation of a 3D line will cover in page 7. So for now, I'm not talking about that yet. Okay. Should ask in chat, would it be helpful if the direction vector is always set to be unit vector? Well, it won't help. It won't help. In fact, setting it to be unit vector will make things more messy. Okay. So we don't bother about the length of the direction vector. Then Rania asks, if lambda can take all real values, will it have decimals and fractions? Also, yes. Yes. If you set lambda to be a value like 0.2, yeah, it will generate also another point on L. So lambda can take decimal values, lambda can take fractions, lambda can even take surds. Okay. Okay. As for direction vector, we would take a vector that is parallel to L, and we would prefer to take a vector where the numbers are all integers. Usually when we have a choice, we would want to have a vector whose components are all integers to be taken as a direction vector to ease our computations. And there's nothing wrong if you want to convert it like, like I know a shorter version of this vector can be minus 0.5, 0, and 1. Hey, of course, there's nothing wrong if you want to take this vector as a direction vector, you can. It's just that when we have a choice, we usually prefer to take the vector that doesn't have any fractions or decimals to ease our computation. And we don't have to care about the length of the direction vector. Whether it has length 1 unit or a longer one, it doesn't matter. Okay. Now let's go back to the notes. Okay. So yesterday, I think I have covered this. By the word line, we are referring to a line with an infinite length. So a line can always be extended indefinitely in this chapter. So to be able to find the vector equation of a line, you must be either given 2 points on the line, or you must be given a point which lie on the line and a direction vector. You must be given either of these two information. You either given 2 points or you're given a point and a direction vector, then only you can get the vector equation of a line. Okay. Now, point number 1 is just a repetition of what I've covered just now in that story. Right, so if you're given a point, a line L that passes through a point which they label as capital A, and the point capital A has position vector small letter a, and vector B is just a vector parallel to L, then you can take A as a fixed point on the line and take B as the direction vector. Then you can write vector equation as R equals A plus lambda B, where lambda is allowed to take all real values. Okay. When writing vector equation of a 3D line, many people tend to forget to write the letter R. It's important to write the letter R here. If you don't write the letter R, then you are not telling the reader what a plus lambda b leads you to. A plus lambda b should lead you to a point on the line L. And to tell the reader that it leads you to the point on the line L, you need the letter R to be there. Because R represents position vector of a general point. So don't forget to write the letter R. It is compulsory to write. Right. So one quick example. If this is line L, this is my point A of 1, 2, 3. My vector B could be pointing this way as long as it's parallel to L. Let's say this is -1, -5, and 2. Okay, then my vector equation of L, it is R equals to 1, 2, 3 plus lambda -1, -5, 2 lambda in R. Okay, don't forget to write this R here as your left-hand side of the equation. Just like when you usually write a 2D line, you need to write y equals mx plus c. You don't only write mx plus c, you need something on the left. So here is the same thing, it's the same idea. Right? To write an equation, there must be something on the left. Right? So here you need R to be the standard symbol on the left. And so R is a standard symbol and the meaning is understood. Okay. Okay, this B though, this B is not a standard symbol though. While R is a standard symbol, this B is not really a standard symbol. And so if you intend to use B as a direction vector, then you should let people know by stating that B is the direction vector. And so usually when presenting my working, I will avoid using the symbol B because it's not really a standard symbol. And a vector B, I mean the letter B could have been used for some other meaning in the same question. And so I usually avoid using the letter B as direction vector when presenting my work, when solving a question. Okay. Some people may choose to write L colon in front. This thing is optional to write. This thing is optional to write. So if you write vector equation of L, then you write this equation, then people will know that you are actually writing the vector equation of the line L. Alternatively, you can write L R equals to 1, 2, 3 plus lambda -1, -5, 2 lambda in R. Then people will also understand that the equation that you are writing here is the equation for the line L. Okay, so what's important here is that when you want to write equation of a line, you need to let people know that you are writing the equation of a line and it's not some random equation. Right, so you need to mention you are writing a vector equation of L, you either mention this phrase in pink or you write the L colon in front if the line has a name L. If you just write R equals to something plus lambda something, without writing, without telling me that this is for line L or some other lines, then it will not be complete. Because in many of the exam questions, there will be more than one line involved, so it's important to specify. Do we also have to introduce the parameter? Actually, no need. Yeah, so if you write, in fact, if you write lambda is allowed to take all real values, then it's already understood that lambda is a parameter. Okay, and just for information, in many of the exam questions, even in past year, they tend to omit this. This one, they tend to omit. This is usually omitted. Usually, Well, technically, lambda in R should be written, but in many of the past year questions, they tend to omit this. So if you see in an exam question, they just say R equals to 1, 2, 3 plus lambda minus 1 minus 5, 2, then the lambda is understood to be the parameter. But technically, it's of course better if you write lambda in R so that people will know that lambda is a parameter. But many of the exam questions, they just omit. And so whenever you see a vector multiplied by lambda or some other symbols, then that symbol will be understood to be a parameter. Okay. By the way, lambda is a commonly used symbol as a parameter. It's not a must to use lambda, especially when two or more lines are involved in the same question. Uh, make it a habit to use different symbols for parameter. If this is line L1, then if there's another line L2 in the same question, let's say this is 2, 3, 4 plus mu minus 3, 5, 2, yeah, mu in R. So if L1 and L2 are involved in the same question, then make it a habit to use different symbols for parameter. Yeah, lambda and mu are the commonly used ones. If there is a third line, then you can of course use whatever other symbols you like lah. Commonly used ones are S, T, U, V, and so on. And so you can use other symbols as parameter as well. It's not a must to use lambda or mu. Lambda and mu are just the commonly used ones. Okay. Right, point number 3 says if a point P lies on the line L, then OP is equal to A plus lambda B for a particular value of lambda. Okay, this is telling you that if you know that a point lies on the line, but you don't know the coordinates, okay. So okay, let's say you are given this line L, okay, and you are given that the equation of line L, the vector equation of line L is, let's say 1, 2, 3 plus lambda minus 2 minus 4, 5, lambda in R. Let's say you are given this equation. Okay. Now, and let's say you are given that point P lies on L. Hey, but you are not given the coordinates of P. But one equation that you can form about P is that you are 100% confident that the right-hand side of the vector equation of the line, it is definitely able to lead you from O to P. Because 1, 2, 3 must be a point on the line. 1, 2, 3 must be somewhere along the line. Right? And the right-hand side of the vector equation is actually leading you from O towards A, and then from, if I call this A, the right-hand side of this equation is actually leading you from O to A, then followed by from A to anywhere along the line L. Right? So an appropriate scalar multiple of minus 2, minus 4, 5. Okay, this is for a particular value. Uh, so a suitable value of lambda. A suitable value of lambda which you need to figure out, it will be able to lead you from A to P. Right, so that means if you know P lies on L, then the vector OP will be equal to vector 1, 2, 3 plus lambda minus 2 minus 4, 5 for a particular value lambda. Right, because taking the vector 1, 2, 3 followed by a suitable scalar multiple of the direction vector, it actually leads you from O to P. That's why the left-hand side becomes OP. Actually, this is one useful information that we will frequently use later in this chapter. Next. Okay, the expression of the form, okay, so this is just a vector equation. So it's known as a vector equation of the line. And so when we talk about the 3D line, we always mention the word vector equation. We don't only mention the word equation, we always mention the word vector equation of the line L. And most of the time, we'll mention the word vector because there is a different form of the equation known as Cartesian equation that we'll cover on page 7. Okay. Now, R is a standard symbol representing the position vector of a general point on the line. The vector A in the printed equation up there is the position vector of a particular point. I usually call it a fixed point, A, which lies on the line. B is known as direction vector. Direction vector can be found by using the position vectors of any 2 points which lie on the line. Okay, so this is telling you that it's not always the case that the question will give you the direction vector. Sometimes the questions are not so kind. Right? So sometimes they just give you 2 points. Sometimes they just give you a line L and they say the line passes through points P and Q with some given coordinates. Let's say this is 1, 2, 3, Q is 4, 7, 8. Then to get a vector parallel to the line is easy. You can always find vector PQ. PQ is OQ minus OP. And then by doing some simple computation, you can get this. And this can be taken as direction vector. And PQ can be taken as direction vector because direction vector is only any vector parallel to L. So if you don't like to use PQ, what other choice do you have? You can use QP also. So QP can also be taken. It can also be taken as direction vector of L. Okay, but if you want to be different, I don't like to use PQ or QP. I want to be different. I want to lengthen my QP. If I don't know what reason, I multiply it by a scalar of 3. That's it. So if you want to take 3 QP as the direction vector of L, can I do that? Yes, you can. 3 QP can also be taken as direction vector of L. Okay, so from this discussion here, we see that direction vector is not unique. Not unique means you can have more than one correct direction vectors. And so different people can use different direction vectors. Although most people will just use PQ or QP, it's not wrong if you want to lengthen your QP or shorten your QP, right, to be used as a direction vector. It's not wrong. Right, so there are infinitely many correct direction vectors. Okay, so the note at the bottom here, Roman 1 and 2. Roman 1 says if A and C are the position vectors of points A and C respectively, and both points A and C lie on the line, then the direction vector can either be AC or CA. This is the same idea as what I mentioned just now in this diagram. I'm using P and Q as a fixed point. Then in your note, they are just giving you A and C as the 2 fixed points. Then of course you can use AC or CA as the direction vector. In fact, if you want to lengthen your AC, shorten your AC, or even take the opposite direction, all of this can be used as direction vectors. Most people will just use AC or CA for convenience. I think nobody would like the trouble of lengthening or shortening it, since that's an unnecessary thing to do. Just use AC or CA. Okay, then next, Roman 2 says the direction vector of a line is not unique, meaning that there can be infinitely many correct direction vectors. If a vector B is the direction vector of line L and B is parallel to B1, B1 and B are 2 different vectors, but then B1 and B are parallel. which means B1 can be written as a scalar multiple of B. Then they say B1 can also be used as the direction vector of line L. So what they're trying to tell us under point Roman 2 here is that so what they're trying to tell us here is that if you are given a vector B that is a direction vector of L, then they say the direction vector is replaceable. It's replaceable by any other vectors parallel to B. And so if I have another vector B1 in the opposite direction of B, then or you have a vector, let's say B2, okay, in the same direction as B but longer, then they are telling you you can replace B by B1 or B2 in the vector equation. Right? So direction vector is replaceable. So for example, I have line L having R equals 1, 2, 3 plus lambda, let's make it minus 1, 1, and let's say 2. Okay, now this is replaceable by any other vectors that is parallel to it. So for example, I know 1 minus 1 minus 2 is a scalar multiple of minus 1, 1, 2. So it is you can use this new vector to replace it, to replace the original direction vector. Okay. I also know like minus 3, 3, 6. And this is also a scalar multiple of the direction vector there. So I can also use this to replace. It is still correct. Direction vector is always replaceable by any other vectors parallel to it. Okay, move on. Yeah, to those who joined the class late today, our class actually started around 7:35 today. So please remember to watch the recording for the part that you missed if you joined the class late. Okay. Then next, okay, moving on to example 1, find the equation of line given a point and direction vector. This one is very easy. Diagram is not required for such questions. As long as they don't ask for a diagram, then diagram is not compulsory. In fact, for three-dimensional vector question, they never ask you to draw diagram. And because it is very hard to draw a 3D diagram nicely. And so they will never ask you to draw diagram for 3D. So don't worry about drawing 3D diagram. Um, Most of the time, I will prefer to still draw a diagram just to ease my computation. So it's up to you whether or not you want to draw a diagram. It's not compulsory, and even if you draw, no marks are given. Okay. So usually for a 3D question, I just simply draw a diagram, because it's too hard to draw accurately. So I just simply draw a line. Okay. Simply draw a line. It passes through the point 1, 2, 0. So I just label a point on the line, and it's parallel to the vector. So I just simply draw a vector parallel to L, and in vector form 1 minus 1, 0. Okay. Right, find the vector equation of the line L. Since you already have a point and a direction vector, it's easy. You can state your answer straight away. No computation needed for example 1. Right, so you just say vector equation of line L is R equals to 1, 2, 0 plus lambda 1 minus 1, 0 lambda in R. Okay, done. Okay, move on to the next part. Example 2. Okay, finding the equation of a line given 2 points of the line. So you are given position vectors of points A and B. So if you want to visualize it, um, you need a line passing through A and B. This time they are not naming the line as L. They are not naming the line as L. So you can't simply use the letter L. Right? So your line passes through A and B, and it can be extended indefinitely. So you just simply draw A and B as two random points on the line. A has coordinates 1, 1, 1. B has coordinates 2, 3, 4, which you can easily read from their position vectors. Okay. Then to get a vector equation of the line, you need a point on the line and also a vector parallel to it. Of course, an easy vector to use is a vector AB or BA. AB or BA can be taken as a direction vector. And so let's suppose that I take AB this time. There's nothing wrong if you take BA. BA would also work. AB is OB minus OA, which is 2, 3, 4 minus 1, 1, 1. That gives you 1, 2, 3. Yeah. So vector equation of the line. Since there's only one line involved in this question, mentioning vector equation of line would be good enough. Okay, if you want to make it more complete, you can of course say line passing through A and B. Okay, so this R equals to bracket plus lambda bracket lambda in R. Okay. The vector that is multiplied by lambda is the direction vector, so you should put in your vector AB here. Okay, it's 1, 2, 3. Then the one in pink should be a fixed point. This is position vector of a fixed point on the line. So it's either point A or point B, whichever you prefer. Okay, I put point A, 1, 1, 1. If you put 2, 3, 4, it's also correct. If you put 2, 3, 4, it's also correct. It can be any fixed point on the line. Okay, then done. Okay, so up until here, you should be aware that when you check your answers for this chapter, um, if your answer look different from the printed answer, or if your answer look different from my uploaded solution later when you do the homework, right? It doesn't mean your answer is wrong. It's possible to get a correct answer for the vector equation of a line that looks different, but it's actually equivalent. So this means if you write, I still talk about this same question here. If your answer is given as R equals to 2, 3, 4 plus lambda 1, 2, 3 is also correct. If your R is given as 2, 3, 4 plus lambda minus 1, minus 2, minus 3 is also correct. So how do you really check that your answer looks different but is correct? First thing to check is the direction vector. Okay. Okay, so if the yellow colored direction vector that you are writing here, if it looks different, as long as it is a scalar multiple of the printed answer, like in this case, your minus 1, minus 2, minus 3 is actually minus 1 times 1, 2, 3. That means your direction vector is also valid. Okay, as long as your direction vector that you use is parallel to the printed one, then it's a correct direction vector. Okay, second thing is to check your fixed point. Now, how to check your fixed point, whether it's correct or not? Okay, the idea is this. Um, So basically, if your answer looks different from the printed answer, after ensuring your direction vector is correct, you should check whether this fixed point is correct or not. Okay. So to know whether your 234 is correct or not, you just need to check that the point 234 is another point on the line. Okay. So to check whether 234 is a point on the line or not, you would sub. Okay. Let's say the blue color answer is the model answer, and you are giving this answer in the green box. Okay. So to check whether 234 is lying on the line or not, you just need to sub r equals to 234 into the equation of line, okay, or so-called the model answer. Okay. Then solve for lambda. Okay. If value of lambda is consistent, then 234 lies on the line. So if 234 lies on the line, then of course your answer is correct. Because you just need to ensure that you are using a point that really lies on the line. So let's try to sub in. So if you sub 234 into the left hand side of the model answer, on the right hand side you combine, you have 111 plus lambda plus 2 lambda plus 3 lambda. You are going to solve for lambda 3 times. Because you have 3 equations, you're going to solve for lambda 3 times. So if all of these 3 equations give you a consistent answer for lambda, then you can conclude that it is a point on the line. If it gives you inconsistent value of lambda, let's say let's say you get lambda equals to 1, lambda equals to 1, but the last one you get lambda equals to 2. That means the value of lambda is inconsistent. So if value of lambda is inconsistent, that means the point doesn't lie on the line. If it lies on the line, you must get a consistent value of lambda. Yeah, so in this situation here, 234 will give you lambda equals to 1, a consistent answer. So 234 is indeed a point on the line. Then your answer is correct. So this is the way to check. Okay. Point, example 3. Okay, let's move to example 3. Okay. So I have just told you the procedure of checking whether a point lies on the line or not. In example 3, we are going to do this exact same thing. So there are questions in the exam that will ask you to check whether a point lies on the line or not. So make sure you know how to check. Okay. So there are 2 tasks here in this example 3. First is to find the vector equation of the line passing through points A and B with the position vectors given. Does the point B lie on does the point P lie on the line AB? Here's the second task. Okay. So let's form the vector equation first. You have point A and B. Point A has coordinates 1, 3, 2. Point B has coordinates 0, minus 1, 4. Get a direction vector. Vector AB or BA can, either one of those will work. 0, minus 1, 4, 1, 3, 2, minus 1, minus 4, and 2. Okay, now for a line that passes through A and B, you can name it as line AB. You can name it as line AB. And so by calling it line AB, it is understood as the line segment AB that is extended indefinitely. So you can say vector equation of line AB is R equals to, Some people will prefer to introduce the notation LAB. This one is optional. L with a subscript of AB will be understood as line AB. Okay, is R equals to a fixed point plus lambda times direction vector lambda in R. That fixed point is either point A or point B. Let's choose point A this time. Then direction vector will just be the vector AB, -1, -4, 2. This one, just bring it down here. Okay, and there you have it, the final answer for your first task. Okay, now to check whether the point P lie on the line AB, we are going to set R equals to OP in the vector equation of line AB. Okay. Some people use the word set, some people use the word let. Yeah, either way will do. Okay, so the idea is you would set R equals to OP in the vector equation of line AB, then you try to solve for lambda. Okay, we have OP equals to 132 minus lambda minus 4 lambda plus 2 lambda. Okay, and what is OP? You just sub in the coordinates. That's -291. So we are basically substituting the point P to the left hand side. It's solving for lambda. -2 equals to 1 minus lambda. This leads you to lambda equals to 1 plus 2. This leads you to lambda equals to 3. Next one, 9 equals to 3 minus 4 lambda. This leads you to 6 equals -4 lambda, which means lambda equals to -3/2. And the last one, 1 equals to 2 plus 2 lambda. This leads you to -1 equals to 2 lambda. Yeah. And this leads you to lambda equals to -1/2. And so clearly these three values are not the same. Then you say, since the value of lambda is inconsistent, or not consistent, we conclude that point P does not lie on the line AB. Okay, done. Not consistent, then you conclude that the point does not lie. Okay, this is a procedure to check whether a point lies on the line or not. Okay, so for you to say that the value of lambda is consistent, it is a must to get all three lambdas to be the same value. If you get let's say lambda equals to 3, lambda equals to 3, lambda equals to -half, even if two of the answers are the same, you still say it is not consistent. For you to say that lambda is consistent, all three answers must be the same. Even if you have two answers being the same, the third one different, you also say it's not consistent. Okay, I think it's the end of the first hour. It's now 8:30. Let's take a break. When we come back from the break, we continue with page 7. I start the timer now. Right, hi everyone and welcome back. Before I continue, I would like to remind those who joined the class late this morning. Our class actually started around 7:35 this morning. If you joined the class late, please remember to watch the recording for the part of the lesson that you missed. Okay, to answer Ranya's question in chat, the latest question asked by Ranya in chat, if two values of lambda are consistent and one is not, well, it actually just means the point doesn't lie on the line. Uh, okay, so let's recall the whole idea of vector equation. Okay, so if I give you the vector equation, okay, I choose very easy numbers. Let's say 1, 2, 3 plus lambda 1, 1, 1. Okay, so this means that you have the point 1, 2, 3 on line, let's call it line L, and you have a vector 1, 1, 1 that is parallel to the line. Now, um, for the case when lambda takes the value of 1, it will lead me to the point 2, 3, 4, for sure. Right, because 1, 2, 3 plus 1 times 1, 1, 1, it will lead me to 2, 3, 4. Right, so this means, and this is actually R. Okay, so when lambda is equal to 1, R will be equal to 2, 3, 4. So what is R? R is a general point. This is position vector of general point on L. So this means position vector means a vector directed from origin O to the point. And so the vector equation will lead me from O to the point 1, 2, 3 first, and then to the point 2, 3, 4. Because I have addition of two vectors. It's one vector followed by the other. Okay. Now, if we take the reverse logic, so instead of generating a point on the line, what if we want to find out whether a given point lies on the line or not? Okay. So let's say they ask you to check whether 2, 3, 4 lies on the line. Okay. Yeah. Of course, we know the answer must be yes. Okay, so now let's try to implement the checking procedure. So what we'll do is we'll set R equals 2, 3, 4 in the equation of L, in the vector equation of L. And then you will get 2, 3, 4 equals to 1, 2, 3 plus lambda plus lambda plus lambda. And then you will solve for lambda. You get 2 equals 1 plus lambda, 3 equals 2 plus lambda, 4 equals 3 plus lambda, which will lead you, of course, to all lambda equals to 1. Okay. Then you say value of lambda is consistent. Okay. So 2, 3, 4 lies on L. Okay. Now, why is it a must for us to get all three lambda to be the same? It is because if you can recall how the point 2, 3, 4 was generated at the top, we're actually setting lambda to be 1. And whatever lambda that you set, it must be the same lambda that gets distributed to all three components. It must be the same lambda that gets distributed to all three components. That's why it is a must for us to get all three the same. Now, if you get two of them the same and one is different, let's say, you would get two of them the same and one is different if I give you the point of 2, 3, 5. For example, check whether 2, 3, 5 lies on L. Okay, the answer will be a no, but let's implement the procedure. Then you would set R equals 2, 3, 5 in the vector equation of L. Then you would have 2, 3, 5 equals to 1, 2, 3 plus lambda plus lambda plus lambda. Okay, so when you solve for lambda, you will get 2 equals 1 plus lambda, which means lambda equals 1. 3 equals 2 plus lambda, which means lambda equals to 1. 5 equals 3 plus lambda, which means lambda equals to 2. This one we say not consistent. Okay. So there's no such thing as x, y on the line, but z is not. There's no such thing. There's no such concept. The point is either on the line or not on the line. That's it. Okay. Because a point itself brings x, y, z coordinate. Like you can't treat x, y, and z separately. Okay. The point itself, x, y coordinate is attached to it. Like the x, y, z is associated with it. You can't separate the x, y, and z. View at them separately. You can't separate them. Right. So diagrammatically, if we refer back to the diagram, it simply means 2, 3, 5 is somewhere off the line. That's it. And so there's no such thing as x, y is on the line, but z is not. There's no such concept. Okay? A point is either on the line or not on the line. That's it. Okay? We cannot treat x, y, and z separately. Okay? If it's on the line, then it's on. If it's not, then it's not. Okay? And so I hope everyone is clear with this. Right, so just remember to check whether a point lies on the line or not, you need all 3 lambda to be the same. You need all 3 lambda to be the same. Reason is because when we generate a point on the line, whatever lambda that you choose, it is the same lambda that gets distributed to all 3 components. And that's why when you perform checking, you need the lambda to be consistent for all 3. Okay, now let's continue. On Cartesian equation of a line, okay. First of all, for your information, Cartesian equation of a line in 3D is actually not formally introduced by the syllabus. A Cartesian equation of a line, what I'm about to cover on page 7 here, I can tell you with 99% confidence that it will not be asked in the CIE exam paper. However, understanding this will be helpful later as you go further into the chapter. That's why I still choose to introduce it to you, although it's not formally part of the syllabus. Kushagra is asking a question in chat, but I don't understand what you're asking. Actually, I don't understand what you're asking. But I think that issue is now closed, lah. And so I will not discuss further on that. And honestly, I don't understand what Kushagra is asking. Right, so let's carry on with this Cartesian equation of the line. Okay. Wait, Kushagra, just now I said the point 235 in the example just now. 235 is not on the line. I draw it externally. 235 is not on L. But it's actually possible. It's actually possible. It's actually possible for the, 2 coordinates to be the same, the third different, but it is on the same line. It's possible. Yeah. I will have to give you a different line there. Let's call this line L2. Okay. Let's say L2 passes through the point, uh, let's put it as 5, 5, 5, right? If the direction vector is 0, 0, 1, then it's possible to have 5, 5, 6 as the point when lambda is set to be 1. It's possible. If you have such a special direction vector, it is possible. So your 5, 5 are repeated. It's possible. It all depends on the direction vector. Okay. Now let's come back to the what do you call it? The Cartesian equation. Yeah. Okay. Now okay. Another reason why I still choose to introduce Cartesian equation to you, even though it's not in the syllabus, is because in the so-called recommended textbook, there is mention about parametric equation, which is this box here. This box on the right of your page, it is briefly mentioned by the so-called recommended textbook. And because this parametric equation is actually closely related to the concept of Cartesian equation, I think I better introduce it, just in case they suddenly go crazy and they want to ask. Right? So although I still believe with 99% confidence that Cartesian equation will not be asked, I think I better introduce it to you. Okay. Right. So to understand the concept of Cartesian equation, um, okay, let's recall the concept of vector equation first. Okay, the symbol r here, the vector r on the left-hand side of a vector equation is a general point on the line. Okay, and we can always replace the general point by coordinate x, y, z in the process of generating, the Cartesian equation. Okay, now let me demonstrate this by using a two-dimensional equation. Okay, I will go back to the story that we talked about yesterday and also earlier today. Where's the story? Yeah, it's this diagram here. Okay. Right, so in this story, the Cartesian equation was y equals to x plus 1. Okay, this is Cartesian. Okay, and the vector equation is this r equals 1, 3 plus lambda 1, 2. Okay. Now, if I want to get vector equation, get from vector to Cartesian, what I need to do is just to replace my r by xy. I have 1 plus lambda, 3 plus 2 lambda. And then I would get x equals 1 plus lambda, y equals 3 plus 2 lambda when I compare component by component for the two vectors. Okay. Then I can try to get rid of lambda by simple substitution. Lambda is x minus 1. Okay. That means y is equal to 3 plus 2 times x minus 1, and I will get 3 plus 2x minus 2, which will give me 2x plus 1. So what I have at the end will be the Cartesian equation. Right, so once you replace your vector r by xy, once you replace the general point by xy, you can get the Cartesian equation. And so that's the whole idea. Uh, in the Cartesian equation, we use x, y to denote the relationship between x and y coordinate for a general point on the line. Because the Cartesian equation, it will be applicable to every point. It will be applicable to every point on the line. Like as you vary the value of x, you can find the corresponding value of y. So the xy in the Cartesian equation is actually the xy coordinate of a general point. So when it comes to 3D, we will apply the same procedure. So if you can understand for 2D, you will be able to understand for 3D. The only difference for 3D is that you get a more complicated form of the Cartesian equation because it's not that easy to eliminate lambda. Okay, for 2D, because we are just trying to combine two equations. Okay, and these two equations, we have a name, we call it parametric equation. A parametric equation refers to equation where x and y are expressed in terms of the parameter lambda. Okay. Now, in the process of combining these two equations to get rid of lambda, when we only have two equations to combine, it's rather easy. And after eliminating lambda, you can get an equation linking x and y. Okay. But when it comes to 3D, here, okay, so let's study this story first. And so the story says that you have a line L that passes through a fixed point with coordinates x1, y1, z1. Direction vector has components a, b, c. Okay, so if you visualize this, the line L will have a point x1, y1, z1 lying on it, and you have a direction vector with components a, b, c. Okay. Now, then you can of course write the vector equation as usual, and then because r is representing the position vector of general point, you can replace vector r by the vector x, y, z. Okay, so after you do this replacement, you end up getting a set of three equations. By comparing component by component. You end up getting a set of three equations. But these three equations, we call it the parametric equations, which is stated here in the additional info box. And we call these three equations the parametric equations of the line because these equations have your x, y, z written in terms of the parameter lambda. Okay. Now, we want to apply a procedure similar to what we did for 2D, where we want to eliminate lambda. We want to eliminate lambda totally from the three parametric equations. Okay, so what we can do is to eliminate lambda totally, right? If you try to make lambda your subject and just sub into the second equation, that's not sufficient because that doesn't really help to get rid of lambda from the third. And even if you, okay, okay, maybe I should paste it over there and scribble a bit. Okay, so now if you don't do this, two steps, okay. Now if you only from the first equation you make lambda your subject, and then you sub this into here, then you are going to get y in terms of x. You will also get z in terms of x. But then you don't have a link between y and z. Because in the 3D equations, it's important to link up x, y, and z. It's just like in a 2D Cartesian equation, you want to establish link between x and y. For 3D, you have to link x, y, and z. Right? So if you just do this, if you just substitute lambda equals x minus x1 over a into the equation for y and the equation for z, you only link up y and z. You only link up yx and zx, but there's no link between y and z. Right? So in order to establish the link between all three variables x, y, and z, to link all the three together, okay, the best way to do this is you would express lambda as a subject for all three equations. Okay? And then, because now if you look at the three equations that I boxed in blue color, the three have the same left-hand side. That means the three right-hand side must be equal. That allows us to equate x minus x1 over a is equal to y minus y1 over b. It's also equal to z minus z1 over c. Okay, of course, all three of these will be equal to lambda. Okay. But then our whole purpose is to get rid of lambda. In the first place, our aim is to get rid of lambda. Then of course we can forget about lambda. We just focus on this. Right. So this will be the Cartesian equation, okay, of a 3D line. So a Cartesian equation of a 3D line, it will have two equal signs linking up three fractions. And so it looks more complicated as compared to a 2D line. And for 2D line, you only have one equal sign, but for 3D line, you have two equal signs linking up three fractions. Okay. So how to do conversion between one form to the other? Thankfully, there is a fast way to do the conversion, and we don't have to really go through the long procedure here every time. Okay, so we're going to apply this fast procedure in the next few pages. Okay. Now, what did we start off with? We started off with okay, we started off with this: r equals to x1, y1, z1 plus lambda abc. And we started off with this. Then at the end, you get the Cartesian being x minus x1 over a, y minus y1 over b, z minus z1 over c, all linked up by using equal signs. Okay, so we know that the r here, it can be replaced by x, y, z. And so that gives you a very quick way, because we are just taking x minus x1, then divide by a. X minus x1 divided by 8, that gives you the first fraction. So if you do the same for the second component, you have y minus y1 whole thing divided by b, you get the second fraction. And do the same for the third component, you get the third fraction. Right, so we are going to use this shortcut procedure here. Right, so here they give you a numerical example. X minus 1 whole thing divided by 1, that's the first fraction. Y minus 2 whole thing divided by 2, z minus 3 whole thing divided by minus 1, and then you link up all the three fractions using equals. That's it. Then same goes when you want to do the conversion from Cartesian to vector. Okay. So sometimes they might make it a bit more tricky. Let's say they give the Cartesian as x plus 1 equals to y minus 2 over 2 and equals to, let's say, 3z minus 3, 3z minus, let's say, 2 divided by 3, something like this. Okay. Now, before you do the conversion from Cartesian to vector, you have to make sure that it is in a form where the point and direction vector is readable. Okay, so for it to be in a readable form, you must have x minus x1 divided by a, y minus y1 divided by b, z minus z1 divided by c. Then only you can extract a, b, c as the direction vector, and x1, y1, z1 as the fixed point on the line. Okay. One important characteristic of this, what I call the readable form, is that your x, y, and z have coefficient of 1. Okay, and it must be a minus. It must be a minus. It must be x minus by a number, y minus by a number, z minus by a number. That means you have to convert it first. X minus minus 1. Since it's not a fraction, you make it a fraction by writing division by 1. Okay. The second fraction is already in a readable form, so that's fine. Y minus 2 over 2, just leave it that way. Wait, the third fraction is not readable yet because you have a 3 in front. Okay, but we know we can always divide the top and bottom of a fraction by the same number, and the fraction would remain equal. Alright, so let's do division by 3 at the top and bottom. We have now z minus 2/3 divided by 1. Okay. So then only this become what I call the readable form. then you can read 1, 2, 1 as a direction vector. And so your vector equation will be R equals to 1, 2, 1, and the fixed point will be the pink numbers above. It's -1, 2, and 2/3. It's the number after the minus. It's a number after the minus. Okay, so this is what we'll do in the next few pages, conversion between different forms. Okay. Find the Cartesian equation of the line AB where point A is this, point B is this. Well, before you can get Cartesian equation, it is easier to get vector equation first. Once you get vector equation, you can get Cartesian easily. Okay. So let's find vector equation first. Okay. So you would need the vector AB lah. Because this is simply a point that passes through A and B. By the name line AB, you know that A and B must be passed through by the line. So AB is just OB minus OA. 217, 384, -1, -7, and 3. Vector equation of line AB. You have R equals to bracket plus lambda bracket lambda in R. Okay, direction vector is -1, -7, 3. The fixed point, just take either point A or point B. I choose to take point A. Then from this form, you can easily do the conversion. This conversion is direct enough that you are allowed to do it just straight away. Right, so Cartesian equation of line AB. Okay. So remember, you will take x minus this number here in yellow and then divide by this number in pink. X minus 3 over -1. Okay. Second component is y. So y minus 8 divided by -7. Third component, z minus 4 over 3. Then link up everything using equals. Okay. But usually in Cartesian form, we don't like to see negatives at the bottom. It is common practice for people to don't like to see negative at the bottom. So what people will usually do is that they will try to make the fraction look nicer. They will try to make the fraction look nicer, and if it's a division by 1, they will just get rid of the fractional form. Okay, so the first fraction they will just write as 3 minus x. So that's a usual practice. A division by 1 can be omitted. Okay. Then for this one, they will just multiply top and bottom by -1 and they write 8 minus y over 7. This is regarded as a nicer form. And then z minus 4 over 3. So this is how people would usually write Cartesian equation. And they will try to make the fraction look nicer. Although when the fraction look nicer, it's no longer in a readable form, but this is actually the preferred form as a final answer. This form is preferred as the final answer. However, it is the line above that is in the readable form. Preferred as final answer. The first line in red is actually the readable form, but the second line in red is preferred as final answer. And to clarify, the term readable is very informal. It's not a very proper terminology. It's just something, it's just a word that I prefer to use. And to describe that it is in a form where you can read the direction vector and the fixed point. Okay. Okay, then next move on to example 5. Vector to Cartesian equation. Okay. Now, in the previous page, there is already one example that demonstrates to you how to convert vector to Cartesian equation. It's supposed to be a very easy thing, but here, um, this question is tricky because the y component of the direction vector is 0. Okay, so first of all, the vector equation, this printed form is a vector equation, but it's not in our familiar form. And because they group terms according to IJK, they don't group terms according to fixed point and direction vector. So we want to regroup the terms first. Okay. So let's rewrite the vector equation. Vector equation of L is R equals to, here they're giving us 1 plus 2 lambda, 2, and 3 lambda minus 1. Now let's single out the fixed point and the direction vector. And let's write them separately. Okay. So 1 plus 2 lambda, I can leave it this way. 2 is just 2 plus 0 lambda. This is minus 1 plus 3 lambda. Just a simple rearrangement of terms. Then you can extract this as 1, 2 minus 1 plus lambda times 2, 0, 3. And lambda in R. Okay. Now, you can of course take x minus 1 divided by 2. There's no issue here when you do the conversion. Okay, so let's write Cartesian equation of L is x minus 1 over 2. No issue here. But the second fraction, y minus 2 divided by 0, this thing is problematic. This thing is problem. Because you cannot divide by 0. A number divided by 0, it will become undefined. So we don't allow division by 0. This is a problem. So that means that when your direction vector has a 0 component, you have to deal with that particular component separately. Okay. So let's try to understand what it means by having a y component of 0. Okay. Now, I will use a simple 2D example first. For your better understanding, I will use a 2D example first. Okay, so if I have a 2D diagram like this, this is a 2D line, 2D line. Let's say this is a point 5. Okay, and this is a coordinate 0, 5. Let's say this is a coordinate 3, 5. Okay. Now, if I call these points A and B, I will have a direction vector which is 3 units towards the right. That will be 3, 0. This can be taken as direction vector. Okay. Now, what it means by having, okay, so maybe I should write the vector equation first. Vector equation of this line, it will be R equals to the fixed point. Let's take point A, 0, 5 plus lambda 3, 0, lambda in R. Okay. Now what it means by having a 0 y component for direction vector is that there is no movement. Okay. This means there is no movement in the y direction as lambda changes. Right, so whenever you change your lambda, that actually moves your point along the line, right? So if you travel along the line, if you travel along the line by varying the value of lambda, um, there's actually no movement in the y direction. In other words, if there is no movement in the y direction, that means y coordinate remains constant for every point along the line. As you can see very clearly in this diagram, the y coordinate of every point, let's say this can be 5, 5. And then a further point can be 7, 5. The y coordinate must remain the same, right? Because there's no movement in the y direction. Okay, so coming back to 3D, the same applies. So when you have a zero component for a zero y component in the direction vector, that means the y coordinate remains constant. And what is the constant y coordinate? The constant y coordinate must be the number 2 here. It remains constant at 2. Y coordinate must remain constant at 2 because you know the point 1, 2 minus 1 must be on the line. You know the point 1, 2 minus 1 must be on the line. And you know that the y coordinate must remain unchanged. Right, so no matter where you move along the line, let's say I move to a point here, I must have whatever, comma, 2, comma, whatever. The 2 must remain. And the y coordinate of 2 must remain. That means you will have to state your y coordinate separately. You will say y equal to 2 separately for such kind of situation. And then your z component is possible to write a fraction, so you would write it the usual way, where you have z minus negative 1 divided by 3, right? And followed by comma y equal to 2. Right, so this is a slightly different way of writing when you have a zero component for the direction vector. Okay. So you have x minus 1 over 2 equals to z plus 1 over 3. Then followed by y equals 2. This is after tidying up the fractions, where the double negative has been converted to a plus. Okay. So this will be the preferred form of the final answer. Okay, any question to ask so far? Clifford asked in chat, is 2 equals x minus 1 over 2? What do you mean by 2 equals x minus 1 over 2? Where does the first 2 come from? No, it is a comma. It is a comma here, which means this and this are two separate statements. Separate statements. You don't link up. You don't link up the first box and the second box. These are separate statements, separated by comma. We don't equate them. We don't equate them. Yeah, so yeah, this should be interpreted as two separate statements. And where the first box is your first statement, second box is the second statement, and you don't link up the two boxes. Yeah. Okay, next is okay, we are done with example 5. Move to example 6. So if you can understand example 5, then example 6 shouldn't be a problem. It's because it's the same thing where you have z equals to 1 written as a separate statement. So that means that the z coordinate of every point on the line is fixed at 1. And, and that's what I write at the hint here. The z coordinate of every point is fixed at 1. That means there is no movement in the z direction as you travel along the line. The direction vector of the line should have a z component of 0. And so if you can understand example 5, this one should be easy. So when you do the conversion to vector equation, it should be rather easy. First is to convert the fractional part to be a readable form first. This one is not yet readable. And this is not yet readable. Especially the second fraction that is not yet readable. Okay. So let's write the Cartesian equation. Convert it to readable form first. X minus 2 over 3 equals to 1 minus y over 2. Z equals to 1 just written separately. Okay. X minus 2 over 3, there's no need to rearrange. This one you have to rearrange at y minus 1 over minus 2. Yeah, then only it becomes readable. Then you say a vector equation. That's r equals to a vector plus lambda times a vector and lambda in r. Okay. The denominators of the fraction, they are all components of the direction vector. 3 minus 2 are the xy components respectively, while the direction vector of the z component in the direction vector must be 0. And because there's no movement in the z direction. And then the z coordinate is constant at 1. That means the z coordinate of the fixed point must be 1 also. This number just transferred over here. Then xy coordinate of the fixed point is easy. You just read the number after the negative at the numerator. So it's 2 and 1 filled up here. 2 and 1. That's it, done. Okay, next we move to the next page, example 7. Okay. Example 7 is to expose you to the idea of changing parameter. Okay. The parameter lambda can be renamed if you want to make the direction vector look nicer. Okay. So the thing is this, sometimes after you do your computation, you end up getting a very ugly looking direction vector, which is of a fractional form, for example. And then if you want to make the direction vector nicer, you can by applying the technique of changing parameter. Sometimes we also call it renaming the parameter. Okay. Um, okay, so the note here says the direction vector is usually expressed in terms of integer. People usually prefer the direction vector to have integer components. Okay, when we obtain a direction vector with non-integer components, we may choose to change the parameter lambda. I purposely emphasize on the word choose here, meaning that it's not a must. It's not a must to make your direction vector nice. If you don't mind having a direction vector containing fractions, it's actually okay. You may choose to change the parameter lambda in such a way that enables the direction vector to be expressed in terms of integers. The changing of parameter, however, is an optional step. Okay. In most of the exam questions, to save ourselves the trouble, we usually don't bother about making the direction vector nice. And in the exam question, if you happen to get a direction vector that looks ugly, we usually don't care. We just leave it that way. Because it's not a must for us to make the direction vector look nice. It's not a must. Right? So this example here is just to expose to you to the idea of how can you make the direction vector look nicer. In the exam, we won't do this unless we are forced. Unless the question says your direction vector must have integer components, or else if they don't say anything, we don't care. The direction vector can contain fractions, there's nothing wrong. In case the question says they want the direction vector to have purely integer components, then only you will try to do the changing of parameter. Okay. Now, I will just demonstrate to you. 99% of the exam question will not force you to make the direction vector nice. So you actually don't have to worry. And this is just to expose you to the idea. Okay. Now you have your Cartesian equation. Cartesian equation given. Cartesian equation of line is x minus 3 over 4, 1 minus y over 2, 2z plus 7 over 5. Convert it into readable form. Y minus 1 over minus 2. For the last one, you have to divide by 2. Z plus 7 over 2 divided by 5 over 2. And because you need to make the coefficients of x, y, z be 1. You can't afford to have a 2 in front there of the z. You have to divide by 2 to make it readable. Then now it is in the readable form, we can write vector equation. It is r equals to a fixed point plus lambda times direction vector lambda in r. The fixed point will be the pink colored numbers. Oh wait, I need. Oh, it's not yet in the readable form. Sorry, I need one more step. I have to change the plus to a double negative. Then now only it becomes readable. Okay, now it becomes readable. 3, 1, and minus 7 over 2 will be the fixed point. R equals to fixed point plus lambda times direction vector, lambda in R. 3, 1, minus 7 over 2, 4 minus 2, 5 over 2. Okay. Since the question doesn't say anything about making the direction vector have integer components, it is actually perfectly fine to leave your answer this way. It's actually okay to stop here. It's actually okay to stop here. Okay. For illustration purpose, to show you how to change parameter, I will proceed further. Okay, but bear in mind that whatever that I write after this in green color is purely optional. It's purely optional. And in the exam, we won't do all these optional things. I'm just showing you how this can be done. Okay. So if you want to do the optional step of getting rid of especially this fraction from the direction vector, what you can do is you factor out a half. You factor out a half so that you have half lambda. This is now 8 minus 4, 5. Okay, and then the next thing you would do is you would replace your half lambda you replace your half lambda by a new symbol. And so that you have r equals to 3, 1, minus 7 over 2 plus, let's call it mu then, 8 minus 4, 5, where now mu takes all real values. And here you say where mu is used to replace half lambda. Okay. Such kind of renaming of parameter is allowed to be done. It's allowed to be done. Okay. So the idea is this: if your lambda is allowed to take all real values, if your lambda is allowed to take all real values, then half lambda, as you vary your lambda, half lambda uh, would also cover all real values. So you can imagine, like, if I draw the graph of mu against lambda, right? Having the relationship mu equals to half lambda, you actually have a straight line with a gradient of half and passing through the origin. Right? So if I allow my lambda to take all real values, which means that I allow the domain to take everything. I allow domain to take everything. Then what is the range? The range is also everything. Right, so that's why when lambda takes all real values, your mu can also take all real values. So that's the idea behind it. Right? When lambda is allowed to take all real values, half lambda would also cover all real values, which you can visualize from the graph. That means it is also possible for mu to take all real values, and that allows us to do the renaming of parameter. Right? Because mu also covers everything. Yeah, the diagram is not required. Like what's important here when doing the renaming is that you introduce mu here and then you tell the reader you are using mu to replace half lambda. Right? Then at the end you can say, yeah, so this now becomes the final answer. Right? The steps in green are purely optional. In the exam, we usually won't do these optional steps. Right? So the purpose of doing this optional step, if you decide to do it, is to make your direction vector look nicer, so that your direction vector have purely integer components. Right? It's just like this. In the exam, we won't do the optional steps. Okay. Now next, example 8, you're given two lines, one in Cartesian equation, the other is just given point and a direction vector. Write down the vector equation, and this one is very easy. Okay, so for your equation of line 1, x minus 1 equals 3 minus y equals minus z. Let's convert it into readable form. X minus 1 divided by 1. This is y minus 3 divided by minus 1. This is okay. This is actually z divided by minus 1. Right? Minus z is the same as z over minus 1. But you can always also minus by 0 at the top. It remains unaffected. And the reason why I want to introduce minus 0 is so that it matches the readable form. And then later I can read the fixed point as 130. Okay. Vector equation of L1. R is equal to a point plus lambda times direction lambda in R. 130 is a fixed point. Direction will be 1 minus 1 minus 1. Done. Okay. Then for line L2, you already have a fixed point. And they say it's parallel to this vector, so this is a direction vector. So you can straight away write vector equation of L2 already. R is equals to use a different parameter. Don't repeatedly use lambda because that will lead to confusion. When you have two lines involved in the same question, use different parameters. So direction vector is 215. Fixed point is minus 217. Okay, done. And so for vector equation of L2, there's actually no working involved because the information is already readily available. Yeah, other than lambda and mu, you are allowed to use any other symbols you like as a parameter. Some commonly used symbols are S, T, U, V, W. Yeah, these are all common symbols that can be used as parameters. Okay, with that, this section is done. We are about to move to a new section on the interaction between a point and a line. Okay, we still have about 20 minutes, so that's enough for me to introduce to you the whole procedure of finding foot of perpendicular and other related things. Okay. Okay. Now let's move to the next page. Okay, so you will see that this chapter is structured in a way that you are first introduced to the line as the line alone. Then we have interaction between a point and a line, and then in the later part of the chapter, we have interaction between two lines. Right, so this chapter is structured in such a way. So we are already done with 9.3.1, which is the line itself, the line alone. Right now, let's see how can a point and a line interact. Okay, so if we have an external point that does not lie on the line, um, as shown in this diagram, there are three things that the question might ask you. First is to find the foot of perpendicular. Right? Second, distance between the point and the line. Third, reflecting the point about the line. So there are three things that the exam question may ask you when you have a point outside the line. Okay. Now, to get the foot of perpendicular, you would follow the procedure in method 1 here. I strongly suggest method 1 because method 2 is actually quite hard to compute. Okay. And in the exam, they are not going to force you which method to use. So don't worry. Right? So if you stick to using method 1 and never use method 2, it's fine. And because the exam will not force you to use projection. So don't worry. In fact, in all of my working, when finding the foot of a perpendicular, I will stick to only using method 1. Because method 1 is the easier one to use. Now, what's the meaning of foot of perpendicular? When we say foot of perpendicular from point P to line L, it means you draw a line that is perpendicular. You draw a line that is perpendicular to line L from the point P. As you can see from the diagram here, there's a 90 degrees made between Pn and the line L. Okay. This point N here, we call it the foot of perpendicular. A foot of perpendicular from P to L. Okay. So from the vector equation of the line, you know that there is a fixed point A with position vector small letter a. You also know that there is a vector B uh, which must be parallel to line L. Okay. So we will make use of the 90 degrees. We will make use of the 90 degrees. Recall that when two vectors are perpendicular, their dot product must be 0. And so we are using this in method 1. Now, let's read through the 4 steps. Okay. So every time I will suggest you to, like later when I do questions, I will suggest you to visualize a simple diagram. And then the first step is to introduce the foot of perpendicular by a name. So here they name it as point N. So in your working, you would first say let N be the foot of a perpendicular from point P to line L. Then only people will know what your N refers to. Okay. Then notice that your point N lies on the line L. Okay. N is a point on line L, which is obvious from the diagram. Okay. So if N is a point on L, then the position vector of N will satisfy the equation of line L for a particular value of lambda. So in our working, we usually use the phrase for some lambda. It means for a particular value of lambda. And the next 3 steps, our aim is to find that particular value of lambda. Then second step is we notice that Pn is perpendicular to L. So we are going to use the information that the vector Pn dot with the vector B, Pn dot with B will be equal to 0. Of course, you can also use Np dot B equals 0. It doesn't matter. Because Pn is perpendicular to B, Np is also perpendicular to B. You can use either one of these two equations in light blue color. Either one will work. Then using this equation, you solve for that particular value of lambda. It will allow you to solve for that particular value of lambda because your On will be some vector in terms of lambda. It will be like a number plus a number times lambda. Something plus something lambda. Something plus something lambda. Right? Then when you find Pn, right? When you find Pn, it will be On minus OP. Right? But because your On contains some lambda, while your OP is a fixed point, then your final vector that you get after doing the subtraction, it will also contain some lambda. It will also contain some lambda. And so when you take Pn dot B, this dot product, when you expand it, it will be a linear equation in terms of lambda, and that allow you to solve for lambda. You can solve for lambda. Once you get that value of lambda, you will sub it back. You will sub it back into this expression for On. then you can get a numerical value for the vector on. You can get a numerical value for the vector on, and that gives you position vector. If they ask for coordinates, then you can easily convert it to coordinate form. Okay, so this is the idea. This page is just to introduce you to the idea first. We will do example questions in later pages. So let me repeat this whole procedure again. Okay. So let's say they want you to find foot of a perpendicular. From, let's say, P1, 2, 3 to L with equation R equals to, let's say, 0, 1, 5 plus lambda 1, 4, 3 lambda in R. Okay. First thing is visualize the diagram. Introduce n or whatever symbol you like as a foot of a perpendicular. Here I introduce f. So I would say let f be the foot of a perpendicular from P to L. Yeah, I'm using an abbreviation PRP here. In that exam, you better write the full word. Okay. Then the next step is to notice that F lies on L. F is a point on L. So F will satisfy the equation. Okay. So when I say F satisfies the equation, it's actually the position vector. Okay. So you will change your R to become OF. Okay. Don't write F equals to, it doesn't make sense. It must be a vector. Okay. So it's the position vector of F that satisfies the equation of L. So you will replace R by OF. Okay. This will be equal to 0, 1, 5 plus 1 lambda plus 4 lambda plus 3 lambda for some lambda in R. This means for a particular value of lambda. Okay. Then the next thing is you would construct a vector either from F to P or from P to F. Okay. Let's say I take vector PF. Okay. Let's say I take vector PF. So PF will be OF minus OP. Okay. Then at the end, you will get something that contains lambda. Okay. Because your OF contains lambda. Okay. Then the next thing is to notice that your vector PF is perpendicular to the line L. Therefore, PF dot with the direction vector 1, 4, 3 is equal to 0. Don't ever say PF dot L. It doesn't make sense. Because the dot product must operate on two vectors. L is not a vector. And so you don't ever say PF dot L. PF dot L is wrong. PF dot with the direction vector is correct. You can say PF is perpendicular to the line. This one is totally fine. It's nothing wrong. The vector is perpendicular to the line. That's fine. But when it comes to dot product, it is a must to involve two vectors. Then only you can have your dot operate on them. Okay. And then from this step, you would then solve for lambda. Okay. So at the end, once you solve for lambda, you will sub your lambda back into this expression. Okay. Sub lambda equal to something back into the expression for OF, and you will get the point F. Okay. So this is the whole procedure. In this chapter, we are going to do this procedure again and again. And so at the end of this chapter, you will be very familiar with this procedure. Okay. Clifford asked in chat, is np.b equals to an.np? Okay. np.b, you're referring to the previous diagram, np.b, an.np. Well, an.np is also 0. Like, np.b is equal to 0 because np and b are perpendicular. Then an dot np is also equal to 0. So yeah, your equation there is correct because both your left and right are equal to 0. But then an dot np is not useful for computation. It's not useful for computation because it's a complicated thing. It's a complicated thing. Because your an itself contains lambda. np itself contains lambda. It's easier to use b because b is purely numerical. And that's why we prefer to use b. If you take an dot nb, I'm afraid you are going to get a quadratic in terms of lambda, which will be hard to solve. We always say np dot b because b is purely numerical. Okay. Now we'll continue with the next part. Okay, the method of using projection, I'm not going to explain this because it's quite hard to implement. Although the formula looks short, but the computation is actually very tedious. And so I'll just forget about method 2 here. Okay. Right. The next part is finding the distance between a point and a line. Okay, the perpendicular distance between point P and the line L is the length of the vector Pn, where n is the foot of perpendicular. So to get the distance from P to line L, the distance is always a shorter distance, so it is always the perpendicular distance. Even if they don't mention the word perpendicular, it's always understood to be perpendicular distance. Right, so to get the shortest distance from point to line, you would first need to find the foot of perpendicular using the procedure on the previous page. Then after you get this point, it's easy to get the vector Pn. Then you find the vector, the length of vector Pn. You find the length of vector Pn. That will be the final answer. Okay. Then in point number 3, in part 3, to reflect a point about a line, you also need to first find the foot of perpendicular. Okay. To reflect a point about a line, you need to make use of the fact that n is actually a midpoint of P and P prime, where P prime is named as the reflection of P in the line L. By the way, P prime is not a standard symbol. So if you want to use P prime in your working, you must introduce it to your reader by using a simple sentence. Let P prime be the reflection of P in the line L. Okay. Then you make use of the midpoint formula, where ON is the midpoint of P and P, where ON is the average of OP and OP prime. And then just by a simple rearrangement of equation, you can get an expression for OP prime. Then you'll be able to compute. Okay. So as a summary for these 3 things covered so far in these pages 10 and 11, we cannot avoid finding the foot of a perpendicular. Right? So the first task is to find the foot of perpendicular itself. And the second task is asking for distance between point and line, but still in the process, you need to first find the foot of perpendicular. And the third task that we cover here is reflecting a point about the line, and it will also involve you to find the foot of the perpendicular first. Right, so foot of perpendicular is very important in our syllabus. Because all the 3 tasks here will involve finding the food. Now, that's the end of page 11. Page 12, we have one example here. I think I won't be able to complete it today. We only have 5 minutes left. So I think I will stop the lesson here today. And I don't want to do this example halfway. Okay, so tomorrow is Saturday. We have extra class. Tomorrow, Saturday, we have extra class. Tomorrow, extra class. Okay, tomorrow is Saturday. Saturday, we have extra class. We'll follow the usual timing, 8:30 to 11. Yeah, it's same time. Same time. In fact, every Friday, I'm going to confirm with you guys about the timing for our Saturday extra class. And so this time, this Saturday, we'll follow the same timing, 8:30 to 11. Also 2.5 hours, where we'll continue from example 9 tomorrow. Right? So whatever that we have covered today, make sure you can digest everything. You might want to revise a bit before tomorrow's lesson start, so that you won't find it hard to catch up. Right? Okay. Yeah, so I'll see you guys tomorrow at 8:30. Tomorrow is an extra class where attendance will not be marked. I strongly encourage you to attend the live class tomorrow if you can make it, so that you don't have to go through the pain of watching recording. Right. See you guys tomorrow. You may leave the video meeting.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir.
Thanks.